Okay, can everybody see the slide?
Yes.
Yes.
Okay, good. So what I'm going to do now, we only have an hour we only have about 50 minutes to go. So I'm just going to give you a flavor for some of the other mechanical caused derailments, but I want to show you how some of them interact with the track as well. So again, we'll talk a little bit more in some of the other classes, but very often what happens is some of the mechanical derailments, for example, some of the bogey type of derailments are often a combination of mechanical and track and sometimes even operating conditions. Again, I'm going to refer you back. Last week, I showed you a website that showed British derailments that allowed you to go through them and look. So if you want to look at light rail, look at metro, look at heavy rail, look at freight, look at passenger, look at rolling stock, look at by type. So this is actually going to be a bogey type of a bogey caused derailment over here. And this is a UK derailment. So this is a little bit more recent. So this was in August of 2017, 12 wagons of a train, of a freight train, derailed at a place called Ely West Junction in the UK. The train was going about 66 kilometers per hour. And this was another case where the train actually derailed and then continued running for another 350 meters, where it did a lot of damage to the infrastructure along the way. And again, as I've told you before by now, this is not uncommon. The driver, obviously was going along for 350 meters without realizing something, but then all of a sudden, because the train started to break apart, there was a loss of brake pipe pressure. One of the brake connectors came loose, and so there was a brake application. So that's when the driver realized there was a problem. And then, he was derailed. This was a freight train, so and the driver was obviously unaffected. So there were no injuries in the accident, but there was considerable damage to the infrastructure. So this was a container train. That should look familiar. This is not dissimilar to what a container train looks like in Israel. Fairly standard UIC type of single stack derailment train, one container train, one container per one level of containers, either one or two containers per wagon, depending on the size of the containers and the size of the wagon. Okay, so this particular accident was not far from London, and it occurred in the intersection of two tracks. So if we look over here, this box here is this green blown up, and you can see the train was actually coming in through here, making this transition, and derailed into just past the switch point. So the derailments, let's see. The wagon itself that derailed had a 40-foot container and a 20-foot container. And when the first wagon derailed, 11 more power wagons behind it. What was found out later was that the 20-foot container actually had the center of the gravity offset longitudinally and laterally. So when it was loaded, it wasn't quite loaded symmetrically. So right away, that sort of tells you there may be an issue here with the loading. But it turned out that the particular bogies that were used in this particular case were a fairly old, well-used class of bogies that have some sort of history of problems in the past. This particular bogie was a standard British type of bogie that's been used in the UK and elsewhere for over 50 years. So what happened was the wagon when it was about 24 meters past the toe of the point. So just about 25 meters past the toe of the point. It climbed on the railhead. So there was a wheel climb. We know it ran on the top of the railhead for a little while. And then went about 12 meters before it dropped into the ballast. And then it was pulled along the ballast for a while. The trailing wheel set also derailed. So it was the leading wheel. So it was the leading wheel of the on the right-hand side that derailed first. Then the trailing wagon, because once it derailed, the wheel set came off at an angle, and it in turn derailed, and then it came across the crossing rail. So it ultimately came across the crossing rail, and caused at that point in time caused a fair bit of damage, and then kept going for about 300 meters, because that's not at all unusual. Okay, so what was the cause here? This particular type of wagon was actually a slightly better than standard type of freight wagon, because not only did it have the primary suspension springs, which all wagons have, it also had a damper. It also had a damping system. So you had a spring, so you had your spring and you had your damper. So that provides a better suspension characteristics normally than a simple but classic three-piece bogie, which just have nothing but a spring set. But when they started looking at the damping pattern, they saw an unusual wear pattern. This is the damping element within the bogie. So this is the damping element over here, which is the damping over here. And what they found was they found excessive wear. And what we found was this particular plunger, which should have been out, should have been all the way out, was recessed inside the bushing. So instead of protruding, it was partially in, which basically means that it wasn't providing the damping that it needed for the vehicle. The spring cap that was supposed to apply the damping load was not functioning because the plunger was not all the way out, and the damping system was ineffective. So in this particular case, what we had was that we had basically a wheel climb derailment, but due to the fact that because the damping was ineffective, the bogie was the wheel was actually lifted up, and it was not providing enough vertical load. So the V on the leading load was dropping close to zero. In fact, there was some indication that there might have been wheel lift before it climbed. So you had a nominal L and a low V. So what does that translate into? A high L over V. The high L over V gives you, of course, your wheel climb problem. So when this is the type of problem that you really need a computer simulation model to follow. And the computer simulation model confirmed the fact that you had a high L over V ratio that was causing this kind of behavior. So basically, your wheel rail contact was such that it was climbing because you had a low V and a high L. High L, V was dropping down, so your L over V suddenly was causing that wheel to climb up. So this was a case where the damping resulted in improper load. The improper damping resulted in improper load distribution across the wheels of the bogie. The leading right-hand wheel had an unloading of the bogie. So while it was going around a curve, because we were going through a turnout, you had a high L, or you had at least a moderate L. You had a low V, and you had a high L over V later ratio. In addition to that, the 20-foot container payload was offset. So it was too far to the right side. So it was also contributing to that, too offset to the left side. So it was also contributing to the high L over V ratio. And then in addition to that, there was some alignment, track twist, cyclic top, gauge variation, cant excess, and rail side wear, none of which by themselves violated any standards. But when they were added into the computer simulation showed that the track quality was poor, the vehicle response was very poor, and the result was a wheel climb derailment. Sensitivity analysis said that if the damping had been working properly, there would not have been a derailment. So the lack of damping was really the main causal factor. Why was there a lack of damping? Maintenance comes back to the issue of improper maintenance. The maintenance inspections were ineffective, and at that time didn't identify that derailment. So this was a case where the immediate cause was there was an insufficient wheel load on the leading right-hand wheel of the wagon to prevent the wheel from lifting. The causal factor, so the cause of the derailment, was the improper damping of the bogie. The damping components were not functioning properly because the maintenance limits had been exceeded, but nobody identified those maintenance limits to identify where the damping system was a component. And that brings us back to some of the underlying issues associated with management or management oversight. So again, the actual recommendations of this were really to improve the maintenance processes, because this was a commonly used bogie with a pretty good history. Okay. So again, the British have a very, very strong emphasis on management oversight. And so again, one of the additional points here was that the management oversight. Here's a similar bogie derailment. I'm not going to go through this in detail, other than to say that in this particular case, what we had was hollow tread wheel on this bogie. So this was the wheel on that bogie, plus the fact that the connector between the body bolster and the truck bolster over here, actually the side plate over here, was missing a roller. And so there were a combination. There was actually a missing bolt on the side frame on the wedge plate here, which is over here. And so this was not functioning properly. So here we had a case where it was not properly taking the load, plus the fact that we had this hollow worn wheel, which was not allowing the wheel to go to properly go around the curve. So it was generating high lateral loads. So what ended up happening, because they were trying to go around the curve, They had inadequate side bearing clearance, so they basically had a high L over V. The hollow worn wheel contributed to the L. The truck bolster contributed to the reduction in V. So again, we had a high L, a low V, high L over V ratio, and so that caused the derailment. Which brings me into the point I really want to make here, which is the L over V ratio. So the L over V ratio, and we've talked about this in the past, we talked about this in an earlier class, is usually used as a safety limit. But I want to reintroduce to you the Nadal equation. So let's look at our wheel rail system. So I have my L and V, my lateral load and vertical loads, which I can break up into a normal component and a tangential component. I have my flange angle, and I know I have friction, mu, between the wheel and the rail. If there's no lubrication, the friction is very high. If there's a lot of lubrication, the friction is very low. I'm not going to go through the mathematics. I think I went through before, but basically, if I took a sum of forces in the horizontal direction, the sum of the forces in the vertical direction, so I basically took the normal component, broke it up into a horizontal and vertical component, took the tangential component, broke it up into horizontal and vertical component, took the sum of the forces in the horizontal direction, took the sum of the forces in the vertical direction, took the fact that the tangential force is equal to mu times the normal force. I can solve for L over V, also known as Y over Q. You remember a lot of the UIC documents refer to the lateral load as Y and the vertical load as Q. So the L over V ratio is equal to, so if I solve basically these forces, the sum of the horizontal and the sum of the vertical, I get L over V is equal to tangent delta minus mu divided by plus 1 plus mu tangent delta, where mu is my coefficient of friction between the wheel or the rail, and delta is my wheel flange angle. And I showed you that also when we were talking about wheels. So the wheel flange angle, remember I said changes with wheel wear. It does not stay the same. So we can start off, for example, at 65 degrees, and it can go down to 30 or 20 degrees, or at least certainly 50 degrees range before to be even within normal standards. So this L over V ratio that I calculate here, tangent delta minus mu over 1 plus mu tan delta, is the L over V threshold, the safety threshold, the level at where if I have an L over V force above that threshold, it's going to derail. So let's sort of do an example and see what happens here. Okay. So if I have a case where I have a wheel flange angle of 65 degrees, which is a fairly common wheel flange angle, and I have it dry. So I have a coefficient of friction of 0.5. That's a dry coefficient between a wheel and a rail. So basically, this is 65, this is 0.5, this is 0.5, this is 65. If you're using an Excel spreadsheet, please convert angles to radians, because Excel, you have to specify in Excel whether it's in angles and radians. And I think the default position is radians. More people get that wrong as anything else. So basically, the tangent of 65 degrees is 2.1445. So L over V is 2.1445 minus 0.5 divided by 1.55 times 2.45, or the L over V is 0.79, or roughly 0.8. So this is my threshold. So if, for example, my vehicle, if I go out into the field and I measure my lateral force to be 50 kilonewtons, no, 50 kilonewtons, and my vertical force to be 100 kilonewtons. Then my L over V is 0.5. It's less than my 0.79 threshold. I have nothing to worry about. But what happens, let's take the British case. What happens if I have an unloading and my V drops from 100 kilonewtons, it drops to 60 kilonewtons. Now my L over V is 50 over 60, which is 0.85, which is greater than 0.79. So I now have a risk of wheel climb. Now, the British analysis said the V dropped much lower, dropped closer to 0. So let's say, for argument's sake, the V dropped to 25 kilonewtons. Then my L over V would be 50 over 25, or 2, which is significantly above 0.79 and have a very high risk of wheel climb. So my Nidal equation gives me my threshold, and my actual L over V tells me whether I'm above or below that wheel climb threshold. And this is the case for both the British derailment and the CSX derailment, the American derailment I showed you. In both cases, the V went down, the L went up. In the CSX case, remember, there was a wheel problem. So there was a worn wheel problem. So that L may have gone from 50 to 70. So again, the L went up. So if the V drops a little and the L goes up a bit, again, I can go from a safe condition of 0.5 to a 0.85, 0.9, 1.0 condition, which is a risk of wheel climb. And I see, and I see my, so this is a sensitivity analysis where I look at, this is the L over V threshold, the Nidal limit, which is calculated from this equation. And in this particular case, the horizontal axis is the flange angle, delta. And these 5 lines or 6 lines represents the coefficient of friction mu. So for the case we did over here, 65-degree flange angle, 0.5 coefficient of friction. So 65-degree flange angle, 0.5 coefficient of friction, about 0.79. If we take, if we lubricated that piece of track and dropped the coefficient of friction from 0.5 to 0.3, then my L over V threshold goes now to about 1.15. So if I would have been in this case, where my L was 50 and my V dropped to 60, and I had a 0.85 L over V threshold, I wouldn't have a problem. I would need an L over V greater than 1.15 to derail in this lubricated situation. And in fact, and I think we talked about this before, this is something that we often see done in wheel climbs in a location where we have a problem with wheel climb, and very often just changing the level of lubrication is enough to bring the threshold up and reduce the risk of wheel climb. Now, another thing that you can do is you can avoid excessive wheel wear. So if I come back here now, so a lot of new wheels will start off as a flange angle of 75 degrees. So again, if I had a coefficient of 0.5, 75-degree flange angle, my L over V threshold is about 1.1. If I allow my wheel to wear down to about a 60-degree flange angle and take that same L over that's threshold, you can see my threshold is now about 0.68. So again, my risk of derailment is higher because I'm dropping my threshold. Is everybody clear on this? I want everybody to understand this because I believe there's a problem that one of the problems that I have on Noodle deals with this. So I want to make sure we understand this.
I think.
Say again? Any questions? Okay, I'm going to assume everybody understands. Yeah, go ahead. I thought somebody said something. Okay, good. Everybody understands it. So again, the Nadal limit is sensitive to the coefficient of friction. If the coefficient of friction increases, the Nadal threshold decreases. And the risk of wheel climb increases. So again, for a dry wheel rail interface or a rough wheel interface. So again, another type of derailment that we run into, that we see, and I think I talked about this maybe in a previous class, I hope, is where we've recently trued the wheels. We've just recently basically machined the wheels. We're leaving a rough surface. That increases the coefficient of friction. Until that surface smooths down, I actually have a higher coefficient of friction. I have a higher risk of wheel climb. And we've seen wheel climb derailments. Again, we've seen wheel climb derailments in metros where this has happened, where the wheel had been recently trued, and that contributed to the wheel climb because the higher coefficient reduced the Nadal limit, the wheel climb threshold.
Professor, I have a question.
Yes.
This Nadal, the coefficient and all the formula and everything, it's useful prior to the train going out from the station. What I mean is, it's useful before to calculate things before to prevent the derailment, or just to analyze after.
The answer is yes. It's used for both. If you're in a situation where you know you're generating very high lateral forces, for example, and so you have a high L over V ratio, then it's useful to do this type of calculation to see where your derailment limit is, to see whether you want to intervene. I have to admit, most of the times I've seen it used after, because people are trying to figure out why the derailment occurred and how to prevent it from occurring.
Mm-hmm.
So that's where it's more commonly used. But from my perspective, either the Nadal equation, or actually, I'll tell you where another place it can be used. It can be used with new vehicle design, even though, quite honestly, some of the better models are much more accurate than the Nadal limit. The Nadal limit, as you can see, is a fairly simple equation. There are good vehicle track interaction models that can calculate your actual L over V's as well. And then you can calculate your actual L over V's generated by a new vehicle, compare it to your Nadal limit, and that can give you an indication that you have a risk of wheel climb derailment, that you have to do something. And you can do a couple of things. You can change the coefficient of friction by lubricating a high risk location, or you can change your wheel flange angle.
Right.
Which
Yes.
what can be commonly done, for example, is you can put your maintenance threshold. You can come up with a threshold that says, I never want my wheel flange to go below 60 degrees.
I understand. Very clear. Thank you.
Okay. So we talked about automatic inspection. Okay, so we talked about some inspection technologies. So we talked about, for example, the wheel profile inspection technology that we talked about can measure the wheel flange angle. But how do we know what the L over V is, for example? How do we know we have a location of a high L over V? So there's a variation. There's a variation of the wild system. Remember the wild system I showed you for measuring V? You can also come up with a strain gauge system for measuring lateral load L. And that combination, in fact, gives you an L over V measuring system, or an L over V technology system, which is just now being introduced into the railway industry. So again, this type of technology is now in its introductory stage. It's past the research stage, it's into the introductory stage. And in fact, you'll sometimes see something called a truck performance detector or a truck hunting detector. Remember, truck is a bogie. The truck hunting detector and the truck performance detector are nothing more than systems that measure LV and L over V. And that combination of LV and L over V will tell you whether you have an improperly performing bogie, particularly one that generates excessively high lateral loads. Okay. So let me sort of finish up with the last couple of minutes and just talk about some of the other car systems and subsystems, and talk a little bit about just give you a couple of more examples of what has to be done. So car body we already talked about. Car body, I talked about the crashworthiness issue, which is an important issue for car bodies or wagons that carry people. And again, my example that I had before, which showed the which showed the German ICE derailment compared to the Hatfield British derailment, where both were 200-kilometer-per-hour derailments, where in one case 100 people died, in another case 3 people died, and one of the attributes for both of them was the crashworthiness property of the car body. So again, that becomes a really important issue for vehicle design. I will tell you that we also have issues with failure of wagon car body as well, but that's a very unusual type of failure mode for railway vehicles, certainly from a derailment point of view. Now, we talked already about some bogie mechanisms, bogie failure that result in L over V. Let me quickly show you a bogie cracking failure mechanism. And this is, again, I picked a Metro because I want to make sure that the Metro people here also pay attention to this. So this is a problem that I actually was involved in with Baltimore MTA, where there was a cracking of the bogie side frame. So do I have a picture of it? Yeah, here I go. So this is the bogie frame. You can see where the axles and wheels go through, etc. And you can see the crack occurred right over here. So this is what they call the journal ring, because this is where the axle and bearing comes out. You can sort of see the crack right over there. This was a case where there was a series of cracks. Approximately 10 of the separate heavy rail transit vehicles had cracks found during inspections. 7 of them occurred within a period of a couple of months of each other. So there was a concern here whether this was a case where all the bogies, just like the case that I showed you with Israel Railways, is this a problem that's prevalent throughout? There was concern that this was going to show up with other bogies. The other bogies were inspected, but only 7 were found to have them in that time period. But there was concern that a few more may happen. So metallurgical analyses were performed and showed this was a classical fatigue failure, but there was no metallurgical cause. In other words, the material properties of the uncracked bogie frame were the same as the side frame. So the concern suddenly became excessive levels of stresses, which means excessive levels of wheel loads, because stresses in wheel loads. There was also some concern in material characteristics or properties from bogie to bogie, but that turned out to be not the case. What ended up being the case was this ended up being a case of excessive loads and resulting in excessive stresses. So the original testing looked at, ended up showing a factor of safety of about between 1.3 and 1.7, should have been sufficient. And basically, there was what ended up happening is the tests, the metallurgical tests were saying that the crack propagation rate that we're seeing in those crack samples was greater than we expected in the original testing. So again, metallurgical tests said there was no problem with the materials. So the question is, was there a loading problem? So in this particular case, they went out and measured the dynamic loading of the fleet. And what they ended up finding out was that there was a subpopulation of wagons where the average lateral load, this is vertical load. So this is dynamic vertical load, was approximately double, or at least 70% higher than the vertical load associated with the bulk of the fleet. You can see the average fleet load was about 3,700, and the average, okay, this says vertical. I'm sorry, this is lateral. This is a typo. This is lateral load. So in these particular wagons, and this was done by real-time monitoring, we're generating lateral dynamic loads about almost double. You can see 6160 versus 3712. These in turn translated into higher stresses, which when put through a fatigue analysis ended up showing that these wagons with a high lateral load had a life of about 580,000 kilometers, as opposed to the roughly 2 million kilometer design load for the 350,000 kilometer design load. Sorry. Yeah. Hold it. Let me take a step back. The fatigue vehicles, the vehicles with the very high lateral loads had a fatigue life of about 580,000 kilometers, or 350,000 miles. The cars, based on the original testing of the vehicle, were supposed to last between 1.5 million and 5 million kilometers, between 1 and 3 million miles. The failures that they observed, the early failures, were occurring at about 660,000 kilometers. So basically what we found here was that there was a subset of metro vehicles that generated very high loads that resulted in premature cracking of the vehicles. And again, this ended up resulting in it actually ended up resulting in a redesign of some of the bogie components to make sure it didn't crack. The factor of safety was as low as 1.15, which was well below what was acceptable for that metro. Okay, I only got a couple of more minutes. Let me show you this particular derailment. Okay. Let me conclude with this particular derailment. This is a braking system failure. What happened is one of the brake blocks fell off the wagon. It basically the brake block fell off the wagon, locked up the braking system. The braking system ended up causing a severe wheel flat. The wheel flat then damaged the rail, damaged the equipment, and then caused basically extensive. It caused the track to derail, and it caused extensive damage to the equipment. This happened to have been a tread braking system where you have a brake pad, a brake block, etc. I'm not going to go through the air brake system. Runaway vehicles usually are associated with failures of the couplers. I'll finish after I finish the slides. I'll show you one video showing you what a runaway looks like. Train overload and imbalance detectors are are basically variations of the wheel load detector, the wild system. So again, if you measure all the dynamic, if you measure the load, the nominal load, not the maximum load, but the nominal load of all 8 wheels, and you find they're non-uniform, you can actually determine whether you either have an overloaded vehicle or a non-uniformly loaded vehicle. That's what I mean by imbalance. It means the wagons are loaded non-uniformly.
Excuse me, Professor.
Yes.
I lost you. If you can go back to side frame cracking.
Oh, okay.
Page. I lost you a little bit.
Oh, okay.
Side frame cracking, and then there was a testing and analysis, and then.
Oh, okay. We're back to okay. All
yes,
right.
Please, if you can explain it again.
Yes.
Briefly. Yes.
Okay.
Thank you.
Okay. So we had the side frame cracking. Oh.
This one. Yes.
So we had that side frame cracking. Okay. The first set of tests that were done were metallurgical to see whether there was a metallurgical problem. There was no metallurgical problem. But what we were finding, these bogies were supposed to last about 1.5 to 3 million kilometers. They were cracking at about 600,000 kilometers. So clearly there was a problem. They were cracking prematurely. After the metallurgical failure was ruled out, they actually went out and instrumented the track and measured the lateral load distribution of all the bogies going of all the wagons on the fleet. And what they found was that there was a subset of wagons, approximately 20% of the fleet, that was generating an average lateral load that was almost double the average load of the rest of the fleet. So there was a subset of vehicles that were generating high lateral loads. By doing a fatigue analysis of the loads, and it's the same fatigue analysis I talked about back in June. So I didn't really want to reintroduce fatigue analysis here. I'm going to assume you all remember everything I said in late June, or you can go back and look at it. But when we did a fatigue analysis based on these higher stresses, what we found was that the calculated life was about 600,000 kilometers, which was very close to the 660,000 kilometers, which was based on testing. Which was based on the actual occurrence of the cracks. This is when the cracks occurred. So the cracks occurred. If we looked at the mileage of the fleet from when the wagons were introduced until when they found the cracks, it was about 660,000 kilometers. The original testing of the vehicle, when they originally tested the vehicle, they expected a life of about 1.6 to 5 kilometers, 1.6 million to 5 million kilometers. So clearly, the life was less than a third of what it was supposed to be. And the fatigue analysis says that, yes, the 580,000 kilometer loads, 580,000 kilometer life that we calculated was very close to the 600,000 kilometers that we saw for the crack to occur. So the result was that there's a small population of bad actor cars, which generated levels of lateral or vertical loads that were between 30 and 60% higher than the fleet average. And there seemed to be a correlation between these cars and the ones that exhibited fatigue failure at about 660,000 kilometers. So there was concern that what we were also seeing was a degradation in performance of the bogies. So they ended up doing a redesign of that structural member to ensure that the stresses were that it can accommodate the stresses associated with the higher level of lateral forces. Is that clearer? Or is it still
much better?
Okay, sorry, I rushed through it much too fast. Okay, I'm out of time, so let me just stop and ask if there are any questions. Anybody want to discuss anything we've talked about? Okay. Next week, we're going to talk about operations-related derailments, which I think you'll find, quite interesting. One of the things I want you to keep in mind here is a lot of the failure mechanisms that we're talking about, like that wheel-rail interaction failure mechanisms, can often be associated with a combination of vehicle and track behavior. So very often the relationship between the performance of the vehicle and the performance of the track have a very strong relationship, not only on derailment risk, but on the load environment and on the fatigue life and the failure behavior of both the vehicle performance and the track performance. And the wheel-rail interface it was sort of a classical example. Okay. Let me. I think it's important that you understand what the other side knows. I think it's very important for track people to understand the mechanical world and mechanical people to understand the track world. And I tell you, I teach mechanical people and safety people track-related issues as well. So I thank you for your patience. I strongly recommend you review the problem that's in Moodle. And you, like I said, it has the first page will be the problem. The second page will be the answer. I think you should. One deals with crack propagation. One deals with Nadal limit. But I think you should have no problems with it. And we'll see you all next week.
Thank you very much. Good night.